Till last class, we had discussed about the ray optics lens. That is only the refraction which takes place in the glass slab, and how to find the refractive index of the different medium, and some relation also we have seen. Next, we are going to study about the lens. Actually, we have to see the total internal reflection, but after the refraction takes place in the spherical lens, then we'll see the total internal reflections. Okay. So the next topic is from the ray optics. The next topic is a lens. So what is a lens? Already we are studying in our 10th standard. So lens is nothing but a transparent medium. Okay, and this is a spherical surface, but the reflections takes place in the both plane surface as well as the spherical surface. To take place the reflections, mostly the surface should be highly polished. Okay, right? But the refraction phenomena takes place in the lens, and a lens is nothing but a transparent medium. A transparent medium which is bounded by two spherical surfaces. Which is bounded by two spherical surfaces. Then the refraction occurs. Okay. So a lens is nothing but a transparent medium that is bounded by two spherical surfaces. There are two types of lenses. One is a convex lens. Another one is a concave lens. So when we can say it is a convex, it is nothing but the two-side transparent medium which is curved outwards. Then it is called convex lens. Okay. So this lens forms a part of a sphere. The sphere has a center which is called as center of curvature. So there only we have mentioned already, which is bounded by two spherical surfaces. So a spherical lens has two center of curvature. Okay. So a convex lens forms a part of a sphere. That sphere has a center which is called center of curvature. Similarly, for a concave lens, it is formed by the two spherical surfaces. First spherical surface having center of curvature C1. Similarly, the second spherical surfaces having center of curvature C2. So a lens is formed by bounding the two spherical surfaces. So this is called a concave lens because both the sides it is curved inwards. So the curved inwards portion is called concave. The bulging outwards portion which is called a convex. Okay. So a spherical lens which have a two center of curvature. Okay. The next term which is related to the spherical lens. Next term which is related to the spherical lens is aperture. What is an aperture? The effective diameter of the spherical lens is called aperture. The effective diameter of the spherical lens is called an aperture. An effective diameter of the spherical lens which is called as an aperture. Okay. So the center of the aperture is called optic center. That is denoted by the letter O. So this is called as an aperture. The center of an aperture is called optic center. What is the O? It stands for optic center. Okay. And already we have seen a spherical lens which has a two center of curvature, that is C1 and C2. Okay. Now the third term which is related to the lens is principal axis, that is a primary axis. Axis means a straight line. So the primary straight line, which is nothing but it is an imaginary straight line that passing through the 2 points. What are the 2 points? Center of curvature and optic center, which is called as principal axis. That is the primary axis. An imaginary straight line that passes through the two center of curvature is called as principal axis. Okay. Next one, principal focus. Okay, I'll repeat once again. First we have seen what is the center of curvature and then about aperture. After an aperture we have studied what is the principal axis. Now principal focus. Okay. Imagine for a convex lens, the light from an infrared object that allowed to incident parallelly on this refracting surface of the lens. These are all incident rays. Then it forms a real image. So to form a real image, the ray which gets refracted and converge a point on an axis, which is called as principal focus. Okay. So principal focus is nothing but the refracted ray appears meets actually a point on principal axis is called principal focus. So a convex lens is also called as converging lens. A convex lens is also called as a converging lens. But in the case of concave lens, the light from an infrared object which is allowed to incident parallel to principal axis, then all the rays get diverged. All the rays get diverged. So all the rays get diverged away from a point. So it appears to meet a point on principal axis since it is called as a diverging lens. So another name of concave lens is diverging lens. Okay. So the principal focus is also over. Next one, the distance between center of curvature to optic center is radius of curvature. The distance between center of curvature to optic center is called radius of curvature. The next one, principal focus. Principal focus is the distance between optic center to, focal length. Focal length is the distance between optic center to principal focus, that is f. Therefore, the relation between radius of curvature to focal length is, if this distance is focal length, then what is this distance? Same. So f plus f, 2f. So the radius of curvature is equal to double of its focal length, or focal length is equal to half of the radius of curvature. Okay. So the various terms related to the spherical lens we have seen. First one, a spherical lens is nothing but it is bounded by two spherical surfaces. So it has two center of curvature. Then distance between the center of curvature to the optic center is called radius of curvature. Before that, aperture. The effective diameter of the lens is called aperture, and the center of this aperture is called optic center. Then the parallel rays converge a point on principal axis of concave lens is called principal focus. So it is converge a light ray. So another name is converging lens. Then focal length is the mean distance between optic center to principal focus. Okay. So these are the terms which is related to the spherical lens. Okay. Next, we are going to see the lens formula. Before that, the concave lens that produces both real and virtual images. Real and virtual image. But concave lens always produce virtual image. Concave lens always produce virtually diminished image. Virtually diminished image. Okay, but convex lens produce both real and virtual image, but the concave lens that produce always virtually diminished image. Okay, so these are the two types of lenses, and how the image forms we are already studied in the 10th. Next we are going to see the lens formula. Before seeing the lens formula, what are the rules used to construct the image formation we'll see. So what are the rules to construct image formation we'll see. Okay, the first one, a convex lens. See, this is optic center, center of curvature, and principal focus. Also, we can say this double the principal focus. Okay, the first rule, the light is incident parallel to principal axis, then it converges through focus. Rule number 1. Second rule, to the same convex lens, This is f2 and 2f2. The light is made to incident through focus, then it refract become parallel to principal axis. And third rule, if light is incident from optic center, in this case alone, the ray goes straight without any deviation. The ray goes straight without any deviation. Without any deviation. Okay. So these are the rules to construct image formation in the spherical mirror, the spherical lens. This is convex lens. Similarly, for a concave lens also we are going to see, but first we'll see the lens formula for a convex lens. Okay. Are you clear about the rule? First rule, light is incident parallel to principal axis. Parallel to principal axis. Then the refractor ray goes through principal focus. Suppose if light is made to incident through focus, then refractor ray becomes parallel to principal axis. But if the ray goes through optic center, it goes straight without any deviation. Okay. So in this point alone, the refraction does not occur. Okay. So they may ask questions. In which point of the lens the ray does not refract now if a light is made to incident through optic center. Okay. This is common for both convex and the concave lens. Next, we are going to see the lens formula. Lens formula for convex lens. Actually, it is common for both concave and convex, but first we'll see for a convex lens. Okay. Optic center, principal focus f1, and this is 2f1, this is f2, and this is 2f2. Okay. So object is placed initially at 2f. Object is placed at 2f. So let us consider AB is the position of object which is placed at 2f. There are two rays start from this object. The first ray, which is incident parallel to principal axis, then the ray gets refracted through focus. Then the second ray goes through optic center, it goes straight without any deviation. So this is the second ray, it goes straight without any deviation. So where the two refractor ray meet, from the point the image is produced. Okay. So the point, the two refractor ray meet from a point from the principal axis, the image is obtained. So this is image, B dash A dash is the image. Okay. Now, so from the point M, let us consider the refraction occurs. Okay, mostly the refraction occurs from the point M. So this is called effective diameter, that is called aperture. Okay. So now we are going to see the two, to compare the two triangles. The first triangle is, see, OBA. OBA and OB dash A dash. OB dash A dash, both also concurrent triangles. So the sides are equal. Okay. So the sides are equal. So what are the two triangles? OBA and OB dash A dash are similar. There is a concurrent. So for the concurrent triangles, the ratios are same. So therefore the ratios are, what are the ratios? A dash B dash by AB is equal to A dash B dash by AB is equal to OB dash by OB. OB dash by OB. This is equation number 1. Similarly, now you compare the other two triangles, that is OF2M and F2B dash A dash. See these two triangles, OMF2 and F2B dash M are similar. So F2OM and F2B dash A dash are similar. That is a concurrent, both also concurrent triangles. So the ratios are A dash B dash by OM, which is equal to F2B dash by OF2. But one small change is we can do that. Already from this ray diagram, notice that OM is parallel to AB. That is OM is equal to AB. So instead of OM, we can change it as AB. AB. So this is equation number 2. Compare these two equations. Which sides are equal? Left hand sides are equal. Automatically the right hand side would be equal. No. Next step, on comparing 1, 2, LHS are equal. Therefore, RHS would be, what is the right hand side? OB dash by OB, which is equal to F2B dash divided by OF2. This is equation number 3. In these equations, we know that for a given spherical lens, all the distance to be measured from optic center. The rules already we have studied, the sign convention. All the distance for a given spherical lens is measured from optic center. So the position of object from optic center is called object distance. That is minus u, because according to sign convention, it is in the left hand side. So the left hand side measurements are taken as minus. But the image formed at the right hand side, so the position of image from the optic center is plus v. Okay. So here optic center and the denominator optic center, and the right hand side denominator also optic center is there. But here alone optic center is missing. So we need to alternate that. So F2B dash is nothing but from OB dash, if you subtract OF2, then it is equal to F2B dash. I repeat once again. This is O, this is F2, and this is B dash. We need what is F2B dash, which means from the total length, if you have subtracted this length, you will get this value, no? So you will get the value. Instead of F2B dash, you can write, that is already OB dash by OB is equal to OB dash minus OF2 divided by OF2. So this is equation number 4. So in this equation, you substitute the values using sign conventions in the above relations. Using sign conventions in above relations. So what you will get? OB dash. What is the OB dash? OB dash is the image distance. So OB dash is the image distance, that is plus b, and OB is the object distance. OB is an object distance, it is minus u. Okay. And OF2 is a focal length. OF2 it's a focal length, it's a plus f. So substitute all the values. OB dash is plus v divided by minus u, which is equal to plus v minus of plus f. So f divided by f. Then using cross multiplications, what you will get? Using cross multiplications, vf, which is equal to minus u into V minus F of, then further you multiply inside. So Vf is equal to minus UV plus UF. Okay. So this is equation number 5. In this equation, completely you divide by UVF on both sides. Okay. So the next step is commonly you divide by UVF. So what you will get by dividing UVF in this equation 5? Equation 5 is divided by UVF. We will get VF divided by UVF, which is equal to minus UV divided by UVF plus UF divided by UVF. And you will get, what you will get? VF cancel, UV cancel, UF cancel, remaining 1 by U, which is equal to minus 1 by F plus 1 by V, or you transfer the two terms. This minus 1 by F you are transferring to left hand side, that become a plus 1 by F, and this plus 1 by U you are transferring to right hand side, already 1 by V is there, so while you are transferring this become minus 1 by U. So we got the length formula. So the length formula is the reciprocal of focal length is a difference in the reciprocal of image distance and object distance. I repeat once again, the reciprocal of focal length is equal to difference in the reciprocal of image distance and object distance. Okay. I hope you are clear about the length formula. Once again I will explain. For a different position of object, we will get the image at a different position. But simple case we will consider. For a given convex lens, object is placed at a 2f. Okay. So object is placed at a 2f. When an object is placed at a 2f, image also formed at a 2f. Okay. So this is the ray diagram. From the ray diagram, we are going to consider the two triangles. The two triangles are the concurrent triangles. First triangle is OBA and then OB-A. So OBA and OB-A are concurrent. So the ratios are equal. So by equating the ratios, we'll get one equation. Similarly, next triangle, concurrent triangles are F2OM and F2B-A'. F2OM and F2B-A'. These two triangles also concurrent, so the ratios are equal. But OM, which is parallel to AB, OM, which is parallel or equal to AB. So instead of OM, we can write AB. You may ask question, sir, why you didn't write OM? That's what, instead of OM, that is exactly parallel to AB, no? So instead of OM, we are written AB. Then compare this equation. Comparing equation 1 and 2, the left hand side are equal. Automatically, the right hand side would be equal. So equating the right hand side, this is the relation. But for a given spherical lens, all the distance are measured from optic center. So here optic center is missing. So in accordance to the optic center, we are rearranging further and then putting sign conventions value, then doing a cross multiplications, we'll get the next step. Then final arrangements, we'll get the length formula. So according to length formula, the reciprocal of focal length is equal to difference in the image distance and the object distance. Okay. Next, we are going to see the length formula for concave lens. The same formula, but for concave lens, how it comes. So how it comes for a concave lens. First we'll draw a ray diagram. A concave lens is nothing but diverging lens. No. This is a concave lens, an optic center, 2f1 and 2f2. This is principal axis and this is principal focus. Okay, let us consider object is placed. So this is the object. The object is placed between 2f and f1. So generally we can say anywhere on principal axis, which means between infinite to optic center. So if object is placed between optic center to infinite, that only I mentioned anywhere on principal axis. In this case of lens formula of concave lens, I kept the object between f1 and 2f1. So two rays start from the object. First ray, which is incident parallel to principal axis, but it is diverging lens now. So the ray appears to diverge by passing through focus. So this is the first ray. Then the second ray, it goes to optic center. It goes straight without any deviation. So the two divergent ray meets actually from a point on principal axis, there only it forms the image. So image is formed here. Since AB is the object and A dash B dash is the image. Okay, A dash B dash is the image. Then as usual, from here we'll draw another one perpendicular. That is nothing but effective diameter of the lens's aperture, and this is the point is M. Okay, as usual. So here we are going to consider the two triangles. What are the two triangles? It is same like a previous case. Like convex lens, how we are considered the two triangles are concurrent. Same like the two triangles are concurrent triangles. First one, ODA and OA dash B dash. Listen. OBA and OB dash A dash are concurrent. So the ratios are equal. The ratios are equal. What are the ratios? A dash B dash by A dash B dash by AB, which is equal to A dash B dash by AB, which is equal to OB dash by OB. This is equation number 1. Similarly, the second concurrent triangles are F2OM and F2B dash A dash. The second concurrent triangles are F1OM and F1B dash A dash are concurrent triangles. Okay, so the ratios are given. What are the ratios? A dash B dash by OM, A dash B dash by OM, which is equal to A dash B dash by OM, which is equal to F1 B dash by F1 O. Okay, but one small changes. OM is parallel to AB. OM is parallel or equal to AB. So instead of OM, we can write AB. This is equation number 2. On comparing these two equations, which sides are equal? As usual, left hand sides are equal, so we are going to equate the right hand side. On comparing 1, 2, LHS are equal, therefore equating the right hand side. What is the right hand side? OB dash by OB, which is equal to F1 B dash by OF1. Both also same, F1O or OF1, both also same. But for a given spherical lens, all the distance are measured from optic center. So we need to alter this term alone. So how can you alter? OB dash by OB in left hand side, but right hand side F1B dash is nothing but From OF1, if you subtract OB dash, you will get. From OF1, if you subtract OB dash, you will get F1 B dash divided by OF1. This is equation number 3. In this equation, we are going to substitute sign convention. So using sign convention, what you will get OB dash. It's the image distance, no? So all in the left hand side. So minus V divided by minus U, which is equal to minus F minus of minus V divided by minus F. So minus minus cancels. So we have V by U, which is equal to minus into minus plus. So V minus F divided by minus F. Next step, using cross multiplication. Using cross multiplication, what you will get? Minus Vf, which is equal to U into V minus F. This U is common for both the terms now, so multiply further inside. Therefore, minus Vf is equal to UV minus Uf. What is the next step? We are going to divide this equation commonly by UVF. This is equation number 4. Dividing equation 4 with the UVF. What you will get? Minus Vf divided by UVF, which is equal to UV divided by UVF plus minus UF divided by UVF. Okay. So minus Vf cancel. Similarly, minus Vf cancel. UV is cancelled. UF and UF is cancelled. Remaining what you have? Minus 1 by U, which is equal to 1 by F minus 1 by V, or this terms you transfer to that side. This both the terms you exchange. What will get? 1 by F, which is equal to minus you are transferring to that side. Yes, minus you are transferring to that side. You will get 1 by U. Already minus is there. 1 by V, or commonly multiply minus on both sides. What you will get? Minus into minus cancel. So 1 by F, which is equal to 1 by minus U minus of minus V. So that only we can write it as 1 by V minus 1 by U. So hence you have got the length formula, the same formula. The reciprocal of focal length is equal to difference in image distance, reciprocal of image distance and the object distance. So we obtain the length formula for both concave lens and convex lens. Okay. So only the concurrent triangles we should take the ratios. After comparing the ratios, we need to eliminate by using sign convention. Then the next step we have to divide by UVF. Only the 4 steps. You need to find the ratios of the 2 concurrent triangles. So for first 2 triangles, for the first 2 concurrent triangles, take a ratios. Similarly, identify the next 2 concurrent triangles ratios. Then compare the ratios with the right hand side. Then use a sign convention. Then divide by UDF. Then rearrange. Only the 5 steps. So it's a very important question. Last previous year they asked this length formula in 3 mark questions, and many times they asked convex lens and from the mirror formula, but this year they removed the mirror formula. So please practice the lens formula for concave lens and convex lens. So from these 2 any one questions they may ask, there is a possibility. Next topic is total internal reflection. That is TIR, total internal reflection. Before seeing the total internal reflection, we will see what is the internal reflection. We know reflection. It's a bouncing back of light from a smooth and polished surface. But internal reflection means, listen, let us consider two different transparent media. One is the optically denser medium. This is optically denser medium. This is separation of medium XY. Okay. So the medium 1 is optically denser, medium 2 is optically rarer. So we have two different media, and the XY is the interface, which means that only separates both the media, that is denser from rarer. Let us consider light must travel from denser to rarer medium. Light must travel from denser to rarer medium. This is normal, so it goes straight. Okay. From this, when a light is traveled from denser to rarer medium, a part of a light is, suppose a light is traveling from denser to rarer, a part of a light is partially reflected back in the same medium, and the part of a light is refracted away. This is called internal reflection. What is an internal reflection? Light must travel from denser to rarer, in which a part of a light is partially reflected in same medium, and a part of a light is partially refracted because to other medium, refracted in a second medium. Then it is called as total internal reflection. But what is the total internal reflection? Now apply the same conditions. Okay, till now we have studied only the internal reflection. The condition is light must travel from denser to rarer. In that part of a light is reflected back in the same medium, and the part of a light is refracted to other medium. But here it is zero. Angle of incidence and refraction is zero. But in this case it is different. And the point of the interface, a perpendicular line drawn, is called normal. So the incident ray which makes angle to the normal is called angle of incidence. And this is a refracted ray which makes angle to the normal is angle of refraction. So this is refracted ray, this is a reflected ray. So when a light is traveling from one denser medium to rarer medium, part of a light is reflected in the same medium, and the part of a light is refracted in the other medium. Then the phenomena is called internal reflection. But what is the total internal reflection? The same conditions we'll see now. Already we said for total internal reflection to occur, we must need two conditions. We'll see what are the two conditions. This is separation of media. Okay, what is the first condition? Condition number 1, light must travel from denser to rarer. This is condition number 1. Now we are going to see how total internal reflection occurs. So light must travel from denser to rarer. Okay. This is incident ray, and this is point of interface. So a perpendicular line drawn is called normal. N and the N dash. What happened? Denser to rarer, now the ray gets refracted away. This is refractor ray. So the incident ray makes angle to the normal is called angle of incidence, and the refractor ray makes angle to the normal is angle of refraction. But further we are increasing the angle of incidence. Further we are increasing the angle of incidence. Angle of incidence. The refractor ray becomes 90 degrees. The refractor ray becomes, which means it goes on the surface of separation, 90 degree. So for which angle of incidence the refracted angle become 90 degree, that is called critical angle. So here theta is equal to 90 degree. Okay. So for a particular angle of incidence, the refractor rate become 90 degree is called critical angle. This is called a critical angle. So the rays, this is angle of incidence for making critical angle. But further this, still you are increasing the angle of incidence. Angle of incidence. Until this cases, most of the rays are partially reflect. But in this case, it won't reflect. Okay, this is partially reflected ray. But for a particular angle of incidence, the refracted angle become 90 degree is called critical angle. Further the critical angle, if we increase angle of incidence, this is n and n dash, n and n dash. There is no refraction occurs, it's fully reflections in the same media, then still increase. Then from the particular point, the reflection only occurs. So these two rays are called, this is partially reflected, this is partially refracted, this is completely, that is internally reflected, that is totally internal reflections. This is totally internal reflections. Okay. So we know the conditions. For total internal reflection to occur, light must go from denser to rarer, first case. And for a particular angle of incidence, the refracted angle become 90 degrees is called critical angle. For a particular angle of incidence, refracted angle become refracted angle become 90 degree is known as critical angle. So further the critical angle, if you increase angle of incidence, further this critical angle, if angle IC is increased, only the total internal reflection occurs. Only the total internal reflection occurs. Okay. So you are very clear about this, I think. So this is partially reflected. These are all partially refracted. But further the 90 degree, for a particular angle of incidence, the refracted angle become 90 degree is called critical angle. Further the critical angle, if you increase the angle of incidence, there is no refraction occurs. It's fully total internal reflection occurs. Still if it goes, then it comes. So because of this, the diamonds are very spectacular in nature. So we are going to see the application of total internal reflections. Okay. The next topic is, before going the applications, we have to see one more thing, the relation between the refractive index and critical angle. Relation between refractive index and critical angle. Relation between refractive index, comma, critical angle. Okay, we know that the refractive index of second medium with respect to first medium, which is equal to, we know that refractive index of second medium with respect to first medium is equal to sin IC by sin R. But conditions, for a particular angle of incidence, the refracted angle become 90 degree, no? Since R is equal to 90 degree, therefore the refractive index of second medium with respect to first medium is equal to sin IC divided by sin 90 degree. What is this value? 1. So sin IC divided by 1. This is equation number 1. Similarly, we can find the refractive index of first medium. Similarly, refractive index of first medium with respect to second medium is equal to, that is reciprocal of refractive index of second medium with respect to first medium. Already we have studied. This product will be equal to 1. So 10th standard itself we have studied. So the refractive index of first medium with respect to second medium is the reciprocal of refractive index of second medium with respect to first medium. Already we found the value. So substitute. Refractive index of first medium with respect to second medium is the reciprocal of this value. That is sin. Yes, what is this value? Sin IC by 1 or refractive index of first medium with respect to second medium is equal to 1 by sin of critical angle. So this is the relation between refractive index and the critical angle. Okay. So next class we are going to study about the application of refractive index and then the lens maker's formula and how refraction takes place in the spherical surfaces.